But you can always shift back once, 1 unit, and just say, start at 0 instead of at 1, and then go 0, 1, 2, 3. So this idea is still there, right? I haven't completely lost you on that. That's okay? So it's a series that looks like this. C sub n. So I'm using C sub n for the first time, right? I've usually used A sub n, but now it's C sub n, and then times x to the n. Ooh, okay, hold on. Now that's different, right? Because what we've been adding up in the past has just been numbers, right? Like that's been some expression, like maybe that's 1 over n, or maybe that's 1 over n factorial, or maybe that's 4 to the n, or something like that, right? We've never had x in the problem, have we? Now we do. And not only is it x, it's x to a power, and that power is n. So let's just take a look at what this looks like. If I start writing this out, so starting with n being 0, right? What would this be? C sub 0 times x to the 0 plus c sub 1 times x to the first power plus c sub 2 times x squared plus c sub 3 times x cubed plus ... And that goes forever, right? Now what is what is x to the 0 power? 1, right? So this first term is really just c sub 0. So assuming now that the c sub n out front is just like we've been doing in the past, these things are going to generate numbers, right? And then this is just going to be x to powers. So this should be some number plus a number in front of x plus a number in front of x squared plus a different number in front of x cubed, and this goes on forever, right? What we have here is a power series, right? That's any series of that form is called a power series. They call it power series because these are powers of x, right? Okay, now, if we fix an x, then this series may converge or diverge.
When you say fix x, do you mean like make it specifically one?
Yeah, that's what I was going to ask you. What do I mean by this? What I mean is, if I actually tell everyone, okay, look everyone, let's replace x with 1/2. Okay? If I replace x with 1/2, then this would be some number times a number in front of a half plus a number in front of 1/2 squared plus a number in front of 1/2 cubed, right? And then keep on going. That might converge or diverge. It depends on what I replace x with, right? Because if I say replace x with 2 instead of 1/2, then this looks different, doesn't it? So if we fix an x, it's going to converge or diverge. Understand? Sure? If x is a value for which it converges, then we can define f of x to be equal to the sum n equals 0 to infinity c sub n x to the n. Okay, what the heck just happened? This is a power series, right? This is a power series. I said that if we fix a value of x here, if I hand you a value of x, then these are just going to be number plus number plus number plus number, right? And that's basically a series that we've been looking at this whole time with all those tests we have, right? So you could try and figure out whether or not this series converges or diverges. But it's got to do one or the other, right? It's going to either converge or diverge, the series. Now, if we say, hey, just consider the x's that make it converge, all right? The x's that make it converge. Then I come in here and I define a function, a new function, to be that power series. Then this is a well-defined function. This right here is well-defined. What do I mean by this? Come on, I feel like I'm losing you.
Geometric?
No. Look, everyone, if I define this function right here, is this well-defined? What do I mean by well-defined? What does it mean? It means that if you give me an input, I give you an output, right? Like if you give me 0, I spit out 0. If you give me 2, I spit out 4. You give me 3, I spit out 9, right? This right here, this series makes perfect sense and will give you a numerical answer, right? If the x you're plugging in makes it converge. If the x you plug into this makes it converge, then you could say, hey, let's call that f of x. So you hand me a number, right? You hand me 2, I spit out an answer. You hand me 3, I spit out an answer. So long as the number you hand me makes it converge. So let's look at another function over here. Is that a well-defined function? Well, it's still well-defined in the sense that I can just look at it and kind of tell what happens. If you give me 0, I spit out 0. If you give me 1, I spit out 1. If you give me 4, I spit out 2, right? You give me 9, I spit out 3. You give me negative 4, right? That would be like, this is a well-defined function, but what if you give me an x that makes it diverge? That's kind of like handing this function negative 4. Understand? That means that this function has a domain. And the domain are the values of x that make it converge. Does that make sense?
So is it kind of like the absolute convergence and conditional?
Nope. With power series, what we're trying to do is we're using the idea that in the last couple of sections, what we've done is we've said, if you give me a bunch of numbers to add up, it's either going to converge or diverge, and I have ways of telling, right? Now what I'm doing is I'm defining a new function. And this new function is going to have you add up numbers. But what this looks like depends on what you're plugging in. If I plug in a number into this, then it's just the last few sections, right? It's either converge or diverge. I'm trying to get us to understand that now what we've done is we've introduced a variable into the series. So now that variable is going to allow us to define a function with inputs and outputs and domains and things like that. Is that We're getting there, okay? I'm just trying to get you to see that we are trying to define this is a well-defined function, this is a well-defined function. We've seen these. These are finite functions, x squared, bump, done. I'm trying to define a new function for you right now that is an infinite sum of things, right? That's new. This is new. It should be weird. Let's just proceed and see how this goes. So the x's which for which the series converges comprise the domain of f. And f in this is an infinite polynomial. This is a polynomial function, isn't it? But it's finite because there's one term. If a power series for which you give me an x which makes it converge will result in an infinite polynomial. You will have something plus something plus something forever, and there's powers of x the whole way out. Let's do our first example of a power series, all right? Because I think, ooh, come on, black. I like to see that move the other direction. I want the American to win, but I like champions that can hold up, over time. Okay, let's do our first example of a power series. First example. Let's define C sub n to be equal to 1. All right. Uh-oh. It'll jump back and forth. That's the computer trying to figure out what's going on. All right. I would like to know what that power series looks like. Okay. So remember, what is a power series? All power series look like this. X to the n, right? That's what I'm telling you, that this particular power series that I'm talking about right now, I'm defining C sub n to be 1 all the time. So isn't this just x to the n? Yes? I'm giving you your first example of a power series where I am defining this right now. I've chosen to define my C sub n to be that. Okay? Now, let's write this power series out. If I plug in 0, what do I get? 1 plus, plus, plus. Okay, plus, dot, 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 forever, right? Does anybody recognize that series as something we've studied already? This is a very special series that we looked at in the very beginning when we first started series. It's kind of hidden a little bit right now, but it's there. It's a geometric series, isn't it? That's right. So look, isn't this, okay, A here for us is 1, isn't it? And then R for us is X. Do y'all see that? So this right here is geometric. Does this converge? If what? If R, but R is not here. It's not R for us. What is it for us? It's X, right? This converges if the absolute value of x is less than 1, right? If the absolute value of x is less than 1. So what I'm saying to you is this. If I were to take and define for you now a function, like over here, and I define this function to be 1 plus x squared plus x cubed plus x to the 4th plus forever. This is an infinite polynomial, isn't it? Now, if I ask you to plug in a number, are you going to be able to spit out an answer for me? Yes, but what? Only if what? Well, it's not always infinite. No. I'm asking you to plug in a number here. As long as the number I'm plugging in here, as long as the absolute value of this is less than 1, right? Then this converges, and you will get a numerical answer. Now, do I know the answer? Not necessarily. Well, it's geometric, so I should be able to get it. But the point is, if I plug in a number, x, where the absolute value of it is less than 1, then this infinite polynomial makes sense. Like, it gives you a numerical answer. It converges to something, doesn't it? As opposed to, like plugging -4 into this. So plugging 4 into this is good, right? Plugging 1/2 into this is good, right? Plugging -4 into this is bad. Plugging 2 into this is bad. Understand? This is a well-defined function and is an infinite polynomial. All right? Now you're asking, like, why does this matter? Where we're getting with this is we're going to be taking a look at functions that we already know and realizing that they are power series. So like e to the x has its own power series. What is it? We'll have to figure out. But every function out there can be represented as a power series. Everything. E to the x squared has a power series. Yeah. You want to be able to integrate e to the x squared? We can do it.
So that's what they'd like to do? Power series integrated?
We'll be able to integrate any function. Yes, we can integrate anything without our techniques of...
So all functions have a power series?
Within, yes. As long... There's some conditions. There has to be, they have to be n times differentiable, so you have to be able to take derivatives of the function. But otherwise, I mean, yeah. All right. So, I just gave you the general definition of power series, right? And you kind of still don't get it, which is okay. Now I'm gonna give you a more general form of a power series, which is going to confuse you even more. The general form of a power series which we call the series about A, looks like this. That should look very familiar. The only difference between this one and the previous one is that instead of having x by itself to the n, I have x minus a to the n. All right? X minus a. So let's see if we can't investigate a little bit about this. Remember, what we want to know is for what values of x will this converge, right? For what values of x will this converge? So let's try this. What if x is a? Let x be a. What would you get here if x is a? Tell me what this series turns out to be. C sub n times 0 to the 0, right? Plus, are y'all with me?
What would it be? C to the
C sub 0, yes. Right? And then, aren't we just going to get zeros the whole way out? Yes?
Because you're multiplying 0.
A minus a to 1.
0 to n.
Basically what we're saying is this. If x is a, this converges. Is that okay? In other words, if that's a 0 in here, we're not adding anything up. And that means it adds up to be nothing, and we've got 0. That converges, right?
Yeah.
All right, so the next part is for us to figure out, what if x is not a? Well, long story short, we don't know. Have to check. And we have to do that for every single power series that anyone ever gives us. So in general, a power series looks like this. If we want to talk about convergence, well, we know if x equals a, we're done. But if x isn't a, we're going to have to figure it out. I already showed you an example of a power series, didn't I? Where I gave you a specific thing. I said C sub n was 1. That turned out to be a geometric series. Now let's look at one that's just arbitrary. Okay, this is just a power series, and what I want to know, well, I'll write it down. what I want to know. Let's take the power series n factorial times x to the n. Now this seems like with an n factorial here that this thing's going to blow up, isn't it? Just explode. Would you all agree? Yeah. But the problem is I don't know what this is doing, right? This could be getting really small and killing off the n factorial. So I need to figure out for what values of x does this converge? Now when we look at this, does everybody see here that this piece right here is our C sub n? Do y'all see that? Okay. That's the part that doesn't have the x in it. The part that has the x in it is this part. Also, can you tell me what A is in this one? A is 0, because a general power series, we have in there C sub n x minus a to the n, right? So with this particular power series, A is, sorry, not A sub n. A is 0, right? Just trying to point that out to you. Now, all right, we got to figure out, how do you figure out if this series converges or diverges? Is it geometric? The n factorial would suggest otherwise. X to the n looks geometric, but the n factorial out front doesn't work. You know what I'm saying? Okay, so what test did I say was the big daddy and that we're going to use a lot? The ratio test. I would like for us to use the ratio test on this. So what am I supposed to do for ratio test? Limit n goes to infinity. Here we go. Let's see if anything I've said here has gone in today. A sub n plus 1, right? So that basically means take that whole sequence in there and replace all the n's with n plus 1s. So that'll be n plus 1 factorial times x to the n plus 1. And then in this case, because that wasn't a fraction to start, I can just go over the original one, which is n factorial, and then x to the n. Let's start cleaning up. You get n plus 1 here, and then n factorial over n factorial, and then times x to the n times x, and then x to the n. So I'm splitting things up. Lots of stuff goes away here, right? Any questions on the breaking up of this thing? N factorial's gone, x to the n's gone. And so here's where I am. I have the limit as n goes to infinity of n plus 1 times x. No, I want us to think about this. Let's just all get up to this point and then let's talk about this. Remember, I'm trying to understand this or view this as a function of x, right? Where if I were to plug in a specific value of x, I'm wondering if it would converge or diverge for that particular value of x. So imagine that we fix x right now. If I fix this x, someone give me an x. 2. Okay, if I fix that x, what does this limit do? It goes to infinity, doesn't it? Give me another x. 1, okay, still, right? How about we use for x 0.000000, 0.00000000 with a million zeros and then a 1 at the end. I have fixed x, haven't I? Okay, that goes to infinity. What happens? It still goes to infinity, right? This thing isn't become infinite, right? Unless I do what? make x 0. If I let x be 0, then this doesn't matter anymore, right? Okay, but didn't we say earlier, the note that I put on the board right before this said that if x was a, it's got to converge, right? So yes, I already know that. If x is 0, I already know this converged. Okay? The question is there anywhere else where it converges? And according to this statement right here, if this is going to be fixed, right, and not equal to 0, then this thing blows up, doesn't it? This goes to infinity, which is obviously bigger than 1. Ratio test. Remember, ratio test? Which means that it would diverge anywhere else. So for what values of x does this converge? No, just 0. Just 0. Just 0. If you plug in any other number other than 0, this thing blows up, and if it blows up, it's bigger than 1, and the ratio tells us that if you're bigger than 1, you diverge. So look at this. You see this right here? This function? This function is a well-defined function that has only one number you can ever plug into it. And the number is 0. And it spits out 0. It's a pretty boring function. Do you agree? It's an infinite polynomial that if you were to try and plug any number other than 0 into it, it would be undefined. It would become infinite. Yes?
Can we plug in infinity or no?
You cannot plug in infinity because infinity is not a fixed number. It's not a fixed real number. Good question. Nope, you're only allowed to plug in finite numbers for x. Y'all have that after Thanksgiving look on your faces. I know, I'm tired too. No, this is important stuff right here. This is... All right, same question. All right, same question. For what values of x does this converge? Can anybody tell me just right away a number guaranteed this converges at? Not 0, not for this one. Yeah, 5 halves. Okay, so if we were to look at this series like this, right? Do y'all see that? Agreed? Now watch, I'm going to go even further with this. Watch. That doesn't look like a power series yet. I know it kind of does. Remember, a power series has to look like this. Sum c sub n x minus a to the n, right? That's what it has to look like? Has to. C sub n can be any function of n. So the problem is that 2 in front does not make it look like that, does it? So watch what I'll do. I'll pull a 2 out, and I'll get x minus 5 halves, right, to the nth power. Can I do that? And now what can I do with this n power with this right here? I can do 2 to the n and then this to the n, can't I? So this can become sum n equals 0 to infinity 2 to the n over n x minus 5 halves to the n. Do y'all see what I did with that 2 to the n? This n power went here and went here, and then I peeled that 2n, put it up on top of that. So that's my power series right there. Do I, I mean, you can see that whatever made this 0 worked, 5 halves. But you can see it more clearly here, I guess. that if I let x be 5 halves, that goes to 0, and then you're adding up nothing, right? So we know for sure 5 halves, but we knew that to begin. We knew that at the very beginning. Whatever makes this thing 0 is one point that we can plug into the function. But are there any others? Right? That's the question. So let's go to the ratio test again. I'm going to erase all this. I'm going to go to ratio test. Because it's the big one. Limit n goes to infinity. All right, and I'm going to be using ratio test. I'm going to do it on this right here. I'm not going to take that cleaned up version. I'm just going to do it on that one right there. So, what's the first part of that going to look like?
2x minus 5 to the
Okay, 2x minus 5 to the
n.
n plus 1 over n plus 1 times, now we're supposed to divide by it, right? But I'm flipping. And on top, 2x minus 5 to the n. This is limit n goes to infinity, 2x plus 5, or minus 5, sorry, to the n times 2x minus 5 again, right? That's splitting that up into two pieces, over n plus 1 times n over 2x minus 5 to the n. I did that so those things would cancel, right? Now watch my next step here. I'll do it down here. I had this n, that, and this left over, right? After the cancellation, those three pieces. I decided to group my n's up over here and put my stuff with the x's over to the side. The reason is because I'm taking the limit as what goes to infinity? N, right? So this doesn't have n in it. This has n in it. Now, what is the limit as n goes to infinity of that? 1, right? L'Hopital there. So if that goes to 1, then doesn't this just equal the absolute value of 2x minus 5? Isn't that what that equals? Now, the ratio test says that you have to take this limit, and you need that limit. In order for this to converge, you need this limit to be what? Less than 1, right? So what I need is for this inequality to be less than 1. If this inequality is less than 1, then this is defined. This adds up to be a number, okay? Now, we need to interpret this result, right? Because we're not done. It's going to get a little ugly here, all right? And we've got about 7 minutes. Let's go. Okay, so the question was, does this converge? We said yes at 5 halves. We said, well, where else? Well, let's do a ratio test. It'll converge so long as this inequality is true. Now, quick review. Quick review. If I say the absolute value of x is less than 2, does anybody know how to rewrite this without an absolute value? No? Okay, time to learn. You drop the absolute value sign, less than 2. Same thing? Greater than negative 2. So if you're saying the absolute value of x must be less than 2, that means that x has to be less than 2 and greater than negative 2. It's kind of like you've got to be somewhere in here, right? You've got to be between negative 2 and 2 for the absolute value of something to be less than 2. Does that make sense?
Oh, yeah. It can be negative.
It can be negative or positive, right? So with that simple little explanation of how absolute values work, this right here simplifies to be what? 2x minus 5 must be less than 1, right? But that whole thing has to be greater than negative 1. Y'all with me? Okay, let's solve for x. Let's add 5 to everything. Add 5 here. 4. 2x. Add 5 here. 6. Okay. Next step. Divide by 2. 2 less than x less than 3. Yes? Okay. If our x is between 2 and 3, this power series is defined. You're still there? Yes. What was the original number we said we could plug in? 5 halves is what? Right in between those two, isn't it? Right in between. Okay, we have one more thing to consider. What if the absolute value of this was bigger than 1? What would happen? It would diverge. But what happens if it's equal to 1? The test failed, right? The test failed. The test fails. So far, here's what we know. We know that the original series that we were looking at, the look on y'all's faces is demoralizing. Okay. Okay, look. This is the original series, right? That's the original one? Yeah. Okay. I'm trying to figure out if I can define this as a well-defined function. What we have determined is that this is a well-defined function so long as the x value you plug in is between 2 and 3, because that will make this inequality true. But I still don't know what if this inequality was equal to 1, because the test wouldn't be able to tell me anything. So what I need to do is now consider what would make this equal to 1. And that would be equivalent to checking these two numbers. If this was 3, right? If I plug 3 in here, what do I get? 6 minus 5, it's going to be 1. Absolute value of 1 is equal to 1. What if I plug 2 into this? 4 take away 5, that's negative 1. Absolute value of negative 1 is 1. That would be equal. So do you see that we are still not done? We have to now check the endpoints. I must test 2 and 3. So I must now test x equals 2 and x equals 3. Did you say this is stupid? Okay. All right. Okay, so first, let x be 2. Let x be 2.
Do we plug that into the original?
To the original problem. Okay, so check this out. If x is 2, then if that x is 2, that's 4 minus 5, which is negative 1 to the n over n. And now this looks more like what we were doing in the last sections, right? No more x's are in there. What type of series is that? Alternating harmonic. That converges how? Alternating series test, right? Or no, you can't do the absolute, because if you do the absolute value of that, it's going to diverge, right? So alternating series test converges, check, right? So if x is 2, we've got convergence, don't we? So guess what? My domain now includes 2. You see that? I can include the endpoint. Now I have to check 3. Let x be 3. If x is 3, this becomes 1 to the n, which is just 1 over n. And that's divergent because it's harmonic. And so I exclude 3. So this function right here has as its domain the interval, closed interval 2, 3. On your final, this is the type of problem you're going to get. Because look what you've had to do. You've had to take this, run a ratio test, right? And then at the end, you had to do 2 different series tests, right? This is like killing 5 birds with 1 stone. All right, I did that all. Look at that. Time's up. So you want to finish your homework for 8-4. We are just starting to dip our feet into the power series. And don't worry, we will integrate e to the x squared. It's going to take us a little while. I believe, if I'm not mistaken, that we only meet 3 more times before the final. So we only